Hello guys, welcome to Backbencher Studies channel. In the last video, we have discussed about the second order system and we already derived different conditions and different types of roots based on the value of this delta over here in this characteristic equation. This delta being the damping coefficient. So we, based on this value of this delta, we can have different types of responses. We already saw that if this delta is equal to 0, that means the damping is equal to 0. That means it somewhat shows the oscillatory sinusoidal behavior. We already saw that. If this delta is equal to 1, that means it is critically damped. We already saw that there is some exponential decay introduced in those sinusoidal decay. We already saw that. So if this delta value lies between 0 and 1, that is the under damped case, the damping is not perfect, but it is little less damped, then how the response would be. Let us uh, do this today. So here we have the characteristic equation which is of the second order. If we give the unit step input to this second order system, then this R of S would be 1 by S over here. So then our system would something look like this. So what we have done is we analyzed this, we we changed this to this equation over here. This S is resulting from this R of S, which is equal to 1 by S, which is multiplied over here. And what we have done is we expressed this as a perfect square, which is of this kind, and we divided, we added del square omega n square, and we subtracted del square omega n square from here. So this is the resulting equation we obtained after manipulating this equation. So you might have familiar with this equation. So we have done that. How we have done that? This is a square plus 2ab. So we obtained b from here, which is del into omega n over here. We added del square omega n square and we subtracted del square omega n square. Then we have a square plus b square plus 2ab over here, which is resulting into a plus b whole square over here, and the other rest of the part over here. So this is how we obtain at this equation. So let us move on from here. So here we have the equation. So if we want to, if we have a quadratic equation which does not have any roots in the denominator, we can write the partial fraction expansion as follows, like this. So we have one equation at s, one pole at s equal to 0. So you can write this partial fraction as a by s over here, and this quadratic equation over here has do not have a roots which are of simplified, which can be simplified. So we can write this as bs plus c by this thing. So if we solve the values of a and b and c, we can get 1 minus 1 minus 2 delta omega n. So if we kind of substitute these values into this expression, we can have the output equation in Laplace domain. If we kind of adjust this one, so that we know that Laplace transform of cos of at is equal to s by s square plus a square. If we kind of multiply this with exponential of minus pt time shifting property, then we can have s plus a, s plus b by s plus b whole square plus a square. Then we have, So if we adjust this in terms of like this, then we can have the inverse Laplace transform formula, and we can easily obtain the inverse Laplace transform formula. So by adjusting this, we have, so this 2 delta omega n can be written as delta omega n, and this delta omega n separately. This is like s plus b by s plus b whole square plus some other a square constant square. So if we apply the inverse Laplace transform of this 1 by s, we can have u of t over here, and this one will result into e power minus delta omega n cos of this thing, which is omega d into t. And if we do this like we have done, we achieved similar kind of adjustment over here for the sign of exponential term. So we can write this term over here as omega d. So we are finally at arriving at this formula. So if we apply inverse Laplace transform at this is kind of straightforward thing. So this gives the cosinusoidal term, and this gives the sinusoidal term, thereby giving us this formula over here. So if we take this exponential term from both of this as common thing, and if we take this one as common, we can have this one and this equation over here, square root of 1 minus delta square cos of omega dt plus delta into sine of omega dt here. So if we assume that this is root of 1 minus delta square as sine of theta, and delta will be the cos of theta, then if we substitute the sine of theta over here, we can have sine a cos b plus cos a sine b, which is of sine of a plus b. So here in this way, we can get a generalized output expression over here. So this is how we can derive the output expression when we have under damping situation, that is when delta lies between 0 and 1. That's all for today, guys. Thank you for your amazing session.